So if we go back and do a little bit of a history before we get started with Laplace transforms, which our study of this is going to, as I said, look a little bit like a math class, and then the second part of it, or as we move from chapter 12 to chapter 13 of the textbook, we'll talk about how we can apply these to electric circuits. So the name comes from a French mathematician, Pierre-Simon Laplace. And he lived between 1749 and 1827. Okay, typical back then. He was a mathematician, astronomer, physicist. Applied Newton's laws to the planets and counted for the deviations in the orbits and things like that. Fairly interesting. And when you look at just the work that we're going to look at in terms of Laplace transform, you probably recognize he thinks at a different level to try and. Usually, it's all I can do just to exercise his Laplace transforms, let alone dream them up to begin with. So, fairly impressive mind. The contemporaries that were working on similar things at the same time would probably be the British physicist Heaviside with his operational calculus and whatnot. So there were other things going on. But basically the Laplace transform talks about, and maybe you've seen this large script L, the Laplace transform of a function f of t could be written as the integral from 0 to infinity of that function f of t times e to the minus st dt. Okay, that's what we're going to spend a lot of time doing. The reason for this is we need a better way of handling this. If you go back to fall term when we talked about transient problems and dealing with RC circuits and RL circuits, we were really limited in the types of circuits that we could do. That was our six-step method. We really couldn't tackle circuits that had multiple equations. So we would like some way of being able to write multiple equations, working on a circuit in the S domain, and coming up with solutions. The notion of a transformation shouldn't concern us or be that foreign to us. So hopefully once we get this transformation done, we'll be able to tackle these circuits as easily, maybe not quite as easily, but almost as easily as we tackled the phasor analysis last term in our AC work. And that's probably a good place to start with our transformation, is the phasor transformation. So we went from the time domain to the phasor domain. Okay, so you've had a little bit of experience with that. Another one, we don't have slide rules anymore, but if you had a slide rule, or you go back and look at the history of the slide rule, when you said that something was equal to two things multiplied together, b times c, you would use a log scale, and you'd look at the log of A being equal to the log of B times C, which would be the log of B plus the log of C. And that's kind of the premise how the slide rule worked. We could answer that then going full circle, that A would be the anti-log of the log of B plus the log of C. And certainly this step here looks a little bit like what you dealt with the Bode plots and the decibel scale and so forth. This isn't something that's just unique to electrical. Transformations happen in a lot of different disciplines. Aerodynamics actually has a lot of transformations, where if you have maybe a wing section you're looking at, see if I can come up with a good wing section here. Something like that, where you'll talk about a leading edge here and a trailing edge. Coming up with the pressures and the velocities across this as air is going over this can be fairly difficult depending on the geometry of that, but they'll have a transformation a Zaworskian transformation in this case, and we'll come up with a circle that's then offset, where you have the leading edge and the trailing edge right there. And you have the flow over that, and the flow over a circle or a sphere is actually pretty well established. So other disciplines use transformations too, so it shouldn't be anything concerning. Well, let's start here and define this a little bit more. So we said that the Laplace transform of f of t, and I guess I just as well fess up, every time I make the script L here, I think of what, Laverne and Shirley. I don't know if you've seen the old sitcoms. You know what I'm talking about. Yeah, she always had it somewhere on her clothes there, script L, Laverne did. So if you're, probably some of you may not have never seen that, Google, or not Google, but YouTube Laverne and Shirley, and you'll see what I'm talking about. But that's the script L. But in our case, it's the Laplace transform, having nothing to do with Laverne or Shirley or Squeaky or Lenny or any of those characters. So so we said this was equal to the integral from 0 to infinity of f of t, e to the minus st dt, where we define s as equal to j omega. Sometimes it's j omega, sometimes they say alpha or sigma j omega. I'm just going to go ahead and say j omega, where s would be equal to j omega like we've used it in the past. Now this is actually read the Laplace transform of the function f of t. And we could also use f of s is equal to the Laplace transform. Didn't do so good on that one. The Laplace transform of f of t. So if you're trying to type this out in an email or something, it's probably a lot easier to use that f of s rather than trying to find that script L and whatnot. A few things to think about in this. It's the integral from 0 to infinity, so it's improper. Usually it will converge. Functions that don't converge, like t to the t or e to the t squared, we usually don't concern ourselves with those things in engineering. So it's from 0, so it's one-sided. And we're going to break things down into two categories. We're going to talk about functional transforms. So those would be transforms of things like sine omega t or e to the minus at, and so on. And then we're going to have operational transforms, where operational transforms might be the transform of f of t or the derivative of f of t dt, and so forth. So we'll look at what those operations look like, or the transform of those look like. Well, to do this, we need to start to talk about how we handle a discontinuity. So let's do that. So let's look at a discontinuity or jump. Okay, so let's say that we have a function here. So there's t, and this is f of t, and it's down here at 0 and then jumps up like this, and we'll say it jumps up some value k. We could talk about this as a step function. So the step function, we could say k u of t is equal to 0 for t less than 0, and k u of t is equal to k, whatever that might be, for t greater than 0. If k is equal to 1, we call it the unit step. And that would be a little bit like turning a switch on. Remember back in those RC circuits where we were turning a switch on at a certain time, oftentimes t equals to 0. We could facilitate that with the step function. We could shift this if we wanted to. There's a little side here. Maybe you have something like this where we've shifted the step so it remains at 0 and comes over to this point like this and jumps up. Maybe it's still jumping up some value of k f of t. So we could say that this in this one we would have k u of t minus a, if this point is a. T minus a is equal to 0 for t less than a, and k u of t minus a is equal to k for t greater than a. And then we could go the other way on this. This could be up and then jump down. Say it jumps down at a. So we'd have k of u t minus a is equal to k for t less than a, and k u t minus a is equal to 0 for t greater than a. Now your author spends some time talking about what happens at a and that discontinuity. Back at this point talking about, well, looking at this, if you have this unit step and talks about a point here that it talks about as 0 minus, and a point here that talks about as 0 plus, and ends up basically averaging the function across that discontinuity. I'm not going to get too carried away with that. I'm going to just mainly talk about those unit steps. Well, let me see if we can put this to use. Questions so far? Well, let's try something. So, what if I have a function that looks, and I'll just draw it over here to give you an idea of what's going on. Maybe it looks like a little blip on the heart monitor. Okay, it comes along like this, and that's it. Okay. It's not a periodic function. I mean, we're used to periodic functions. That's what we do to FOIA, but all this remains at 0. All of a sudden we have a little blip like this, and then it goes back to 0. So I guess it's probably not what you'd want to see on the heart monitor. You get one heartbeat out of it, and that's it. Okay? It's not a periodic function. It has this little blip and then continues on. So what I'd like to do is write a expression for that, and I'd like to use the unit step, or not necessarily the unit step, but the step function to do that. So let me quantify this a little bit better. So I'm going to say that this is t in seconds. And we're going to say that this all of a sudden pops up at 0, goes up, and then it comes back down, then it goes up, and then it's all over. Okay, we'll say that this is 1, this is 2, this is 3, this is 4. Okay, and we'll say this goes up to a value of 2 and down to a value of minus 2. And you can put whatever function we'd want here. And you could put any function you want. We'd usually use voltage or current in the disciplines we talk about. So basically it's linear with breaks at 0, with a break at 1, with a break at 3, and a break at 4, right? So if I look at the slopes on this, this has a, what's the slope on this? +2, is that right? Whereas the slope on this is -2, and the slope on this one then is again +2, if I think about slopes. So let me try something. Let me try thinking about this a little bit differently. And at this point, if I introduce a function that has a +2 slope, and then at 1 I introduce a function that has a -4 slope, because +2 and then a -4 gives me that -2 I'm looking for, right? And then at 3 I introduce what? I'm going to have to introduce something with a, hopefully a straight line, with a +4, and then when I get to 4, what is it going to have to be? Again, let's see, a -2, isn't it? Yeah, -2. Okay, so -2 slope. So let me write this out in a little more detail. So I'm going to say this one here is 2t u of t, and then at, so that's going to be at 0, and then at 1, I'm going to have this one that's going to be -4 t minus 1 u of t minus 1, and then at 3, I'm going to need this one, which is what? 4 at t minus 3 u t minus 3, and finally the last one at 4 is going to be that one, which is going to be -2 times t minus 4 u of t minus 4. So if I put this all together, taking this, I can write the function f of t is equal to, and I'm just going to sum these up. I'm going to take 2t, I mean, wouldn't that be the equation of that line that has a slope of 2? 2t u of t minus, then this one, 4t minus 1 u of t minus 1, then plus 4t minus 3 u of t minus 3, and then again minus 2t minus 4 u of t minus 4. So that's actually how I could build that discontinuity in that graph, using the step function like that. That'd be a little bit like just turning switches on and off to get that. So we got the switch being opened or closed. We've got that represented with the step function. Now let's start to talk about some of these functional transforms. We'll hold off and do the operational transforms later, but let's look at some of the functional transforms. So the first transform I'd like to look at is the unit step. So we're going to take this thing and look at this going from maybe this point here across there to there. We'll say that that is 0 minus, and we're going to say that this point is 0 plus. That's a unit step, so this is 1.0. So if I talk about the Laplace transform of the unit step, that's going to be equal to the integral from minus, or 0 minus, should be consistent how I write that, 0 minus to infinity of f of t e to the minus st, which I could really say the integral across here. I mean, if I look at the area across here, the integral across there is what? The integral from 0 minus to 0 plus is 0, isn't it? Okay. So I could rewrite this as actually the integral from 0 plus to infinity, which that works good because that's something I can think about. I don't have to go across that discontinuity. And that's maybe just making too much of something. But now I can put my function in here. What was my function? The unit step. So the function is 1. That's the unit step. Then I have, by definition, e to the minus st dt. So this turns out to be equal to then e to the minus st divided by minus s. Is that right? Evaluated at 0 plus and infinity. Yeah. You differentiate that and you get back to that. Yeah, that works. Okay. So when you evaluate this, this turns out to be equal to what? The upper limit gives me 0. The lower limit's going to give me 1 over s. So I have 1 over s. Which is important. That is the Laplace transform of the unit step is 1 over s. So we'll do a few of these, and then I'll just put up a table of some of the common ones. Let's try this one. This occurs quite a bit. Is we'll look at decay. So we'll say that we have a function here, e to the minus at, like that. So we'll say for it's 0 for t less than 0, and then it's e to the minus at for t greater than 0. So we can come up with a Laplace transform here. Laplace transform of e to the minus at is going to be equal to the integral. And I can do this same trick here, so I'll just say that it's from 0 plus to infinity of e to the minus at, e to the minus st by definition, dt, which would give me what? The integral from 0 to infinity, and we could say 0 plus if we wanted to, e to the minus, what are we going to have? A plus s t dt. Which looks an awful lot like this, doesn't it? So we could say this is actually 1 over s plus a. So that one comes up quite a bit. If you have this function here, that's what the Laplace transform is right there. Yeah, because the reason I'm saying this is 0 is because we're trying to get these points no distance from that. So that's why the horizontal distance would be 0. Let's see, we'll do one more. We'll try and just sum all of the functional, or a lot of the functional ones that we would need. Let's see, do they have? Yeah, that'll be good. Okay, so let's try a sine wave. So we'll try something like this. Let's say that we have something at 0, and then all of a sudden we have something like this. and then it carries on. So I'm going to try and do the Laplace transform then. Maybe I'll do that down here, the Laplace transform of sine omega t. So that's a sine wave. So I'm going to say it's equal to the integral from 0 to infinity, and that would be 0 plus. I won't bother writing the plus. We've been through that enough. So we have then the sine of omega t e to the minus st by definition dt. That looks like one of those ugly ones, doesn't it? Well, a couple of things. If you do quite a bit in math, you probably may remember these. If not, you probably want to try and remember them. In general, the sine of alpha could be expressed as e to the I alpha minus e to the minus I alpha divided by 2I, and that cosine of alpha is equal to e to the I alpha plus e to the minus I alpha divided by 2, where of course I is, I'll write this over here, I is equal to j is equal to the square root of minus 1. So I put them in as i's because you usually see them in a math book like that, but to be consistent with what we've done in the past, they would be j's. Have you seen those? Yeah. Yeah? Okay. Those are going to be pretty handy getting you out of trouble. They're going to get us out of trouble here, in fact. So I can write this from 0 to infinity of the sine. So I'm going to say this is e to the j omega t. So I've swapped the I for j omega t, minus e to the minus j omega t, all divided by 2j. And then I'm multiplying this whole thing by e to the minus st dt. So I could say that I have integral of 0 to infinity of 1 over 2j times e to the minus s minus j omega t, and then when I multiply the other one, I have a minus e to the minus s plus j omega t dt. So I could say that this is really 1 over 2j. I could take that out of the integral, and then these others look a lot like what we just had, right? That looks an awful lot like that. So I think I can use that and say that we would have 1 over s minus j omega minus 1 over s plus j omega. I guess it should be consistent in my brackets. Something like that. So if I go through and I get a common denominator, I can tidy this up a little bit. What would I have? 1 over 2j times s plus j omega minus s minus j omega divided by s squared plus omega squared. I think that's what I would get. And I'll get to cancel out those, right? Yeah. So then I'd have 2 of these up here. What would I have? I'd have that negative and that negative cancel, so I have 2j omega cancels with the 2j there, so I'd have omega in the numerator. Omega in the numerator, and s squared plus omega squared, which I think is my final answer. I'll keep that. That one I don't think comes up all that often, but that's how we do it. You do the cosine similarly. The j omegas don't cancel. Well, this is a negative. I guess I probably should have been more careful. Let's see, this negative here, so I should probably say, yeah. I think we're good now. So we spend the rest of the term going through these functions. You'll probably do quite a few in math here in a few days. Let me just list out some of the more common ones and what the Laplace transform is, so we can go on with this. So a list of functional transforms. So I talk about f of t, and then over here we'd have f of s, or if you prefer, the Laplace transform of f of t. Okay, so we could talk about the unit step, which we said was what, 1 over s, and the t, I could just talk about t, which is the ramp, which is 1. And these you could go through and derive these just like we have done in the past. E to the minus at, didn't we do that one? That's the exponential function, which is 1 over s plus a. We saw that. We have a sine of omega t, which is sine function, which is omega over s squared plus omega squared. We just did that one. Must be cosine hanging around, which is our cosine s divided by s squared plus omega squared. Then we have t, e to the minus at, which is a dampened ramp. And that is 1 over s plus a quantity squared. Make sure this lines up. And then I don't know that these come up too much, but let's look at a dampened sine, e to the minus at times sine omega t is the damped sine. And that is omega divided by s plus a squared plus omega squared, and finally the damped cosine. This will be our last one as we run out of room. Damped cosine s plus a in the numerator divided by s plus a squared plus omega squared. Yeah, I think we're good with it. So we did this one. I think we did this one. We did that one. You could go through and prove all of them to yourself if you wanted to, and you could just keep going with different functions. But these are some of the more common ones that we will use. Well, that's our functional transforms. So let's switch gears and look at operational transforms then. And really, we could have got stalled out. I mean, we could have spent the rest of the term doing this, different functions and whatnot. Operational is a lot more concise. There's only a certain number of operations that we use. So those are going to be multiplication by a constant, addition and subtraction, differentiation, and integration. We'll just put those together. There'll be two separate operations, but just if we're keeping inventory on this. Translation in the time domain. Translation in the frequency domain. And finally, scale changing. So those are the ones we're going to look at. Probably we use the ones on the top quite a bit more and less as we go down that list. Well, with that, let's just go ahead and get started. So I'm going to just go through these basically rules. If I have multiplication by a constant, doing the first one. I could say that if the Laplace transform of f of t is equal to f of s, then the Laplace transform of k f of t, that constant k f of t, is equal to k f of s. So multiplying by a constant is the same. Then let's do addition and subtraction. So if the Laplace transform of f1 of t is equal to f1s, and the Laplace transform of f2 of t is equal to f2 of s, and the Laplace transform of f3 of t is equal to f3s, then we could say that the Laplace transform of f1 of t plus f2 of t minus f3 of t, that should do it all in one fell swoop, is equal to f1 of s plus f2 of s plus f3 of s. Okay, so we add and subtract them the same in the frequency or in the time domain as we do in the frequency domain. So we've got multiplication by a constant, addition and subtraction. Now we need to do differentiation and integration. Let's.
So kind of last one, even though it was addition and subtraction, it's still.
Yeah, I'm glad you called me on this. This should be. It's same. So if this is addition, that's subtraction. That should be subtraction. Yes, thank you. Everyone get that? Okay. So let's try a differentiation. So with differentiation, let's say that the Laplace transform of the derivative of f of t dt is going to be equal to s times f of s minus f at 0, or 0 minus. Okay. So for the first derivative, we would just take the function in the s domain and multiply it by s, and then subtract the initial value. If you go with a higher order, it gets a little more complicated, but this was probably going to be the most common, although I should probably put this down. You'll definitely see this in math. The Laplace transform of a higher order, so we have d to the nth derivative of f of t dt to the n is equal to S the n fs minus S n minus 1 f0 minus S n minus 2 d f of 0 minus dt minus the derivative n minus 1 f0 minus dt n minus 1. I don't think we'll be using that term, but I guess if we're going to do differentiation, you should probably show that. It's a lot of work because you're going to use it again for each time you have each order of the derivative. This is luckily the one that we're going to use. Integration is the real deal. You might say, well, differentiation, that's turned differentiation fairly easy to do, although on some of the functions it might not be that easy. It's turned it into some kind of a mess, although this is not that bad. But integration is the real bargain here. So if I look at the Laplace transform of the integral from 0 to t of f of, let's say, x dx, what that is f of s divided by s. So the Laplace transform of an integral ends up being division. Division is quite a bit handier than integration. So there's your real bargain. This we could say was multiplication with a starting value. We don't want to forget about that. But this one's pretty simple, just division. Well, those are ones that we're going to use an awful lot. This first one for differentiation, this one for integration, those come up a lot. The ones that don't come up so much, translation in the time domain. So translation in the time domain is that the Laplace transform of f of t minus a, so I've translated it a, of u t minus a is equal to e minus a s f of s. If I translate it in the frequency, so translating in the frequency domain, the Laplace transform of e to the minus a t f of t is equal to f s plus a and then the last one I think we had was scale changing. Which is good for modeling, I guess, but I don't know that we'll use this that much, but we'll put it down here. F of AT is equal to 1 over A F of S over A. So if you want to speed things up or slow them down, you can. I wouldn't worry so much about these. I would concentrate on the integration, the differentiation, the addition, subtraction, multiplying by a constant. And those are quite a bit easier to think about. Well, let's put some purpose to this, and we'll take our operational transforms and our functional transforms and try and put them all together in a problem, because it'll be a little while before we're back for lecture again. I don't want to leave this hanging around too much. So let's say that we start with a problem like this. This is going to go back to a problem like we might have seen first term in our transient problems. So we'll talk about some current, some DC current source here. And we've got a switch that we open up, which is probably a good thing we open it. In real life, we wouldn't want to short out a current source, but at t equals 0, we open that thing up, which is good news. We've got our resistance. We've got our inductance. We've got our capacitance. And we have then the voltage across here, V of t. Okay. So if I want to come up with an expression for V of t, let's see if we can do that. So I'm going to keep this really easy and assume no initial energy storage. So the inductor is not storing energy, the capacitor is not storing energy initially.
Saying there's no voltage process
Initially, yes. Yeah. We haven't charged the capacitor up. It's discharged when we put it in there. So let's see. If I want to talk about the current through the resistor, what's the current through the resistor? Maybe I better put this in time domain. Yeah, I'll put it as a script V of t. So what's the current through a resistor? Let's see, Ohm's law. V is equal to IR, right? So I is equal to V over I. Let's use our variable, so I could say V of t divided by R. And I'm just doing a Kirchhoff's current law up here, summing up all the current. What's the current through a inductor? And that was what, 1 over L. You're doing this in physics now too, aren't you? Okay, 0 to t of V of t dt. Is that the current through the inductor? And then what about the current through a capacitor? That current through the capacitor? Okay, so I got the current through the resistor, the current through the inductor, and the current through the capacitor, and that had better equal what? It had better equal the current of the source, IDC, the source there, and I'm gonna deal with this switch. I'm gonna say U of t. There's the switch. Okay. And that's what we had essentially in the transient problem. Actually, this is tougher than the transient problems we did because we could only do resistive inductive or resistive capacitive, right? The next chapter that we didn't have time to get to in the fall talked about R, C, and L, and that was a more challenging equation to solve. So what I'd like to do is, I don't think we're going to finish this, but we can start on our way. We're going to need some operational transforms. So we're going to have multiplication by a constant, because it looks like I've got some constants, some C's, and some 1 over L's. So that was the Laplace transform of K f of t is equal to K times Fs. I'll need that one. I'll need the Laplace transform of the integral 0 to t f of t is equal to f of s over s. That's the real bargain that we talked about, division. Then the Laplace transform of the first derivative. That was the easy one, remember? Which is f or s f of s minus f at 0. So that's the operations. We've got multiplication by constant. We've got differentiation. We've got integration. Then the last thing we have is we have the step function. What's the Laplace? So these are our operational, and then our functional. Maybe put a line here, keep those separate. What was the Laplace transform of the unit step, or the step function? 1 over s, right? Okay, so whoops.
Step function. Functional Laplace transform is because of the switch. Right?
So now when I put this all together using this and this, combining all of that, I can come up with, this is going to look like V in the S domain divided by R plus 1 over L times, how do I do an integral? Right there. So I'll say it's Vs over S. Okay. Because our function is a voltage function, that's why I've switched the F's for V's. Then how do I do differentiation? So I'll have plus C times, what am I going to have? S times V of S minus V at 0. And what's that whole thing equal to? I have to do this right-hand side, don't I? I ran out of room. IDC times what? 1 over S? So I was looking for this V of t. Now I'm going to look for the V of S, and I'll have to eventually get back. Let's see if I can finish this up then. So I've got this thing here. So let me rearrange this a little bit. Factor this V of S out. And I have what? 1 over R plus 1 over LS plus, let's see, this term here goes to 0, right? We said there was no initial energy storage, so that would be 0. So I have then, maybe I should be clear on that, from this, I know that this is 0, because we had no initial energy storage, that's 0. I have to be more careful with that in the future. So if that goes to 0 and I factor a Vs out of there, I'm just left with C times S, right? Is equal to IDC times 1 over S. So if I solve for V of S, I know that's IDC divided by, let's see, I think what I'll do is multiply both sides, or multiply this whole thing by S over C. Is that fair? Yeah.
Don't you know that I left the switches with the U and T?
Because that was our function to turn, because that was our function that introduced the discontinuity.
How would you?
Because when this thing is closed, what's your current? 0, right?
Yeah.
And then when you open the switch, what's going to happen? Current's going to jump up. Does that look like what we had with the step? Yeah.
So what would it look like if it was a different one of the functional transforms?
Well, that we would change this if this was some exponential source. Then this term would change. Okay. So I'm going to come back over here and I'm going to multiply, that was the rule, I multiply both sides. So I'm going to multiply this side here by S over C. I multiply that side there by S over C. So when I do that, maybe I better not be so hasty. Let me get rid of this. Okay, so when I do that, I have V of S. And then I'm going to have what? I multiply this by S over C. I'm going to have S over what? RC. Plus, then this is going to, the S's will cancel, and I'll have 1 over LC. And then lastly, I'm going to C's will cancel, and I have s squared is equal to IDC divided by the s's cancel, and I have 1 over c. So I'm dividing that by c, or multiplying by 1 over c. So if I solve then for v of s, it's going to be IDC divided by c divided by, and I'm going to rearrange this denominator just a little bit, s squared plus 1 over RC times S plus 1 over LC. Okay, so if I wanted the answer for V of S, that would be it. I unfortunately don't want the answer for V of S, I want it for V of T. So the next step is we're going to say that V of T is equal to the inverse Laplace transform of V of S.
So we would be saying that we're converting into the time domain?
We're going back into the time domain, right? And this is the inverse Laplace transform. Which is really a whole nother lecture. We're going to do things, you can see this polynomial in the denominator there. We're going to get to use partial fractions, so that should be fun. And we'll come up with that and we'll get V of T. But this is, once we get this method working, you'll see it's going to be quite a bit easier and adaptable to much more complicated problems than we had with our 6-step method. So when we get together next time in lecture, which will be after the exam, we're going to talk about how to do an inverse Laplace transform. We don't have those skills right now, or we haven't talked about those skills. We'll talk about how to do that, and then we can come back and finish this problem up. But I wanted to go on this problem, even though I know we couldn't finish it, so that you could see why we're doing this. Why did I talk about the operational transforms? Why did I talk about the functional transforms? That's so that we could get it into the S domain and solve it in the S domain. Now we just have to get it out of the S domain, and that's going to be the area of the inverse Laplace transform. So once we have that, the class will start to look a lot less like a math class, and we'll start to then look at circuits like this or more complicated and see what we can do with it.